Good day everyone, welcome to this video. In this video I'm going to show you how to code interrupts in a PIC18 microcontroller, specifically external interrupts, timer interrupts, and UART receive interrupts, and basically combining them together into one code. So first off, I'm just going to do a brief overview of exactly what this code does. So essentially this is the main function, which is an LED connected to pin RA2, and what happens there is that just stays on forever. As you can see, it's just that, and go to main. This is essentially a while run loop. It's an infinite loop. And then in the interrupt section, basically three interrupts are combined, which is the receive UART receive interrupt, a timer interrupt, and lastly an external interrupt. So what happens is, once the code starts to run, every 500 milliseconds there'll be a message on the screen through the UART terminal to signify that 500 milliseconds timer interrupt has occurred. And also there's an external timer interrupt where you connect a push button to the controller, and once you press the push button, it's going to signify an external interrupt has just triggered. And of course the last one is the receive interrupt. So once you type something on the screen, it's going to echo, essentially signifying that it received whatever you typed into it. It's going to echo back what you typed into it, basically. Alright, so that's the overview of the code, what the code does anyway, just to keep that in mind. And this is, I'll just start from the top. The title interrupts, you include the configuration bits. Obviously we're using the internal oscillator. RC6 and RC7 are regular pins according to this. Watch the timer is off. MCLR, using external MCLR pin enable bit, and low voltage programming is on, and everything else is just default. And after that we have a C block, and the C block is I actually don't think the C block is necessary for this particular code, but it's there anyway. So, and also for this, and next we have org 0x4. So every time we start the code, basically what this command does is it writes this particular string, right? It writes that to that program memory location. So every time the code starts, it automatically writes this to this particular location. So essentially at the program memory at hex 4000, the first that register hex 4000, you're gonna find this there, which is actually 13 in decimal. So you're gonna find 13 in that register. And 0x4001 or 0x4002, you're gonna find a space, and the next register you're gonna find the T, next one I, etc. And then it's gonna come down to ext int. The reason this is initialized to this way is because it helps a lot when writing a string to the terminal. Instead of writing each individual one, T, I, M, E, R, sending that individually, it works much faster just doing it this way. And obviously there's a code to accompany it, which I'm going to show you in a minute. Well, actually more than a minute, but it's going to be in this video as well. And next I have the start of the code, 0x00h, go to init, and org 08h, go to ISR. So this 4 lines is standard, and they're required to start the code. To be honest with you, I don't think I remember the exact explanation at this point in time for these lines, but you can check the other videos. The video on UART, I probably explain these 4 lines over there. Anyway, but these lines are necessary. This, okay, I think I remember now. So this is to tell the code where to start. So essentially, when you program this, your entire code, this assembly code, gets turned into hex, into a hex code, which is just I guess a simplified form of binary code, a more understandable form of binary code. So that gets loaded into your microcontroller, and this tells I guess this IDE where to start, where it's gonna start from, where your code is gonna start to running from. So essentially, the first code that's gonna be run is init. So as you can see, it's 00H. So that means in your program memory, because that's actually where your code is stored, it's gonna start storing the code from this line, which signifies the start of your code. And for the ISR, it's gonna start storing the code from 08 hex, which is way below. So it's go from that point, it's just gonna jump to ISR. Yeah, and that's that. And alright, so let me just change this to capital letters. Alright, so in initialization, we initialize the oscillator, which is 4 megahertz in this case, and then we initialize the interrupt, then the timer, and the UART, and then the port. So let me start with the OSC init. Obviously that's oscillator speed is 4 megahertz. I'm sure it's in the data sheet somewhere. Actually, let me just check that quickly. So if you go to the oscillator module, and yeah, on page on page 30, yeah, on page 30 of your data sheet, you find it there. You find the initialization for your oscillator. We're using 4 megahertz, so that's going to be 101, and that's exactly what's done in the code here. And the next is the interrupt init. So for the interrupt, here we're just initializing the what you call it, the external interrupt. So to do that, you need to clear the incon register. So the incon register controls the interrupt. It's the interrupt control register, and first off you need to clear it, and then you set to the GIE, which is global interrupt enable, and then you set the PIE, which is peripheral interrupt enable. That's to enable the peripherals, which is required for the timer, I believe, and also I think the external interrupt as well. And specifically for the external interrupt, you need to enable int0IE, which is this, and clear that, because you don't want that, you don't want the interrupt getting triggered now. So, and as well, also what's important is the interrupt pin is tied to an ADC as well, so you need to make sure that the ADC is disabled, and for that particular interrupt pin, it's RB0. We're using RB0 in this example, and to know what ADC is tied to it, you have to go to and you have to go to table. No, is that it? I think that's it. Let me see, just to be sure. Oh yeah, it's you have to go to table 3. You have to go to table 3, which is on page 7. So on table 3, as you can see, you look under IO, you see RB0. Let me just zoom in, and it might not be clear. So you look on your IO and you see RB0. As you can see, it's tied to AN12. And also if you look here, that's int0. So that's what you have to worry about. You must what you call it, you must disable analog functionality for that particular pin. an AN12. And how do you know that AN12 is attached to ONSL B? Because it's port B, so it's going to be the analog control is going to be ONSL B. So ONSL B AN12. So you disable that, and then once analog functionality is disabled, now we need to operate the pin as a digital input. So say BSF TRISC-B 0. That sets it up as a digital input. And after that, also for the timer, for the timer 0, in this case we're using timer 0, and it's going to be incon, using incon and then TMR 0IE to enable the timer 0 interrupt. And as well, we need to clear the interrupt flag. So this particular interrupt flag, what it does is it goes high. This goes high automatically once the interrupt has been triggered. So right now the interrupt's not triggered, so we just clear it. And sometimes we can actually affect the how do you call it, whether the interrupt is triggered or not in code. So that's why it's very important to clear it, because I know for sure the external interrupt, you can actually, if I say BSF here, it's gonna trigger right away. It's gonna trigger that external interrupt right away. It's actually that I've seen that before. I'm sure about that. And so that's the interrupt init. You'd notice that there's no interrupt initialization for the receive. That's done in another function. Yeah, that's explained further in another video, I believe, your art video. But anyway, I'll look at that function again. And so now we just go for the timer 0 init. Well, let me not skip. But yeah, for the timer 0 init. So for the timer 0, because we want a 500 millisecond interrupt. We want a 500 millisecond interrupt. So essentially what we do is, let me just go to timer 0 module, register. So this is the T0 con, timer 0 control register, and 1 to 500 millisecond delay. So there's a particular formula we use to actually calculate that, and let me just show you that formula quickly on Notepad. Let me just zoom into that, make sure it's clear. I'm trying to zoom into this. Alright, okay, it's working now. Great. So this is the formula you need to concern yourself with. So essentially what you need to know about timers is this, right? So first off, the PIC, the timer uses the timer is 4 times less faster than the PIC. So what does that mean? It means each timer count is gonna be, so before I talk about the timer count, let's just look at the clock, the oscillator period, the period of the oscillator. So the frequency of the oscillator is F or C, right? That's the frequency, and then the period would be 1 divided by F or C, right? And now the timer uses 4 times less than this. So the timer requires the timer is 4 times less fast than the oscillator. So the timer frequency is F or C divided by 4. So which means timer period is 4 divided by F or C. So basically it takes 4 times longer. It takes 4 times longer than the 4 times slower than the oscillator, essentially. So so each timer count, the maximum of each let me not say the maximum, the lowest time, the minimum time required for each timer count is this right here. Is 4 divided by FOSC. So obviously if this is much faster, if this is higher, FOSC is higher, the timer, the less we can make each timer count. But in this case the FOSC is 4 megahertz. So essentially we use this particular formula to obtain the time required, that we require. So let me just break down this formula quickly. Let me just do that and make this the focus. I'm gonna make this formula the focus. Alright, so you just focus on this formula. So the timer can operate in 8 bits or 16 bits, and in 16 bits then the maximum count is going to be 2 to the power of 16, right? So which is going to be 65536, right? But we're starting from 0, and 65536, when you actually write it out, I think it's actually more than 16 bits. It's actually more than 16 bits. So in this case the maximum will be 65535 because we're starting from 0. Alright, so 65535 with so I've explained why this is 65535. Let me just do this so there is no confusion. Alright, so this is the maximum count for a 16-bit timer right here. And what we want to do, right, if we want a specific time, so the timer by default starts counting from 0. So if we want a specific time delay, right, a specific time for our timer interrupt, let me say, for our timer interrupt, we have to modify the time at which the timer actually starts. So let's say, let me make an example. So let's say we're counting from 0 to 16. Let's say the maximum of the timer is 16, right? So let's say the time it takes from 0 to 16 is that it takes. This is just isolated example. Let me actually just move this example away from everything so we don't confuse them for one another. Let's say that a timer, the maximum count of a timer is 16 counts, right? And we're counting from 0 to 16, counting from 0 to 16, from 0 to 16, right? Let's say the time it takes from 0 to 16 is 1 millisecond, right? But now we don't want 1 millisecond. 1 millisecond is too slow for us. We want much less time. So what do? We start counting from 8. Let's say we want 500 microseconds, or half of this. Let's say what we want is actually, we want 0.5 milliseconds instead of 1 millisecond, right? So 1 millisecond, we want 0.5 milliseconds. What do? We start counting from 8 instead of 0. So then 8 to 16 will give us 0.5 milliseconds. Okay, and let me just press the wrong thing there. 0.5. Alright, so that's 0.5 milliseconds. If we start counting from 8 to 16. And yeah, so that's the working principle of the timer, of this timer. So maximum 16 counts, it's going from 0 to 16. We're getting that's 1 millisecond, but we actually want 0.5 milliseconds. So what do? We start count, instead of start counting from 0, we start counting from 8, right? And that's exactly what we do in this case. So the time from 0 to 6 to count from 0 to 65535 is actually a lot longer than 500 milliseconds. So but we want 500 milliseconds, so we have to start counting from a specific point. And this YYXX, let me actually write them in capital. So this YYXX, so there are 2 registers for the timer, TMR0L. For the timer, for timer 0, it's TMR0L and TMR0H. So XX, this one goes into TMR0L, YY goes into YY goes into TMR0H. So we have to load a specific value that we want there, and then start the timer, and then turn the timer on, and then it's gonna start counting from that point to 65535. In essence, giving us the delay required. And so this is the formula. So this this formula is basically saying the number of counts, which is this 65535 minus YYXX, multiplied by the time for each count, required for each count, multiplied by a prescale. So sometimes it's not enough. So once we just do this for multiplied by the period, the time is still too small. The time is still too small. But when we multiply by a prescale, we'll give ourselves more how do you say it? We're able to get more time. Basically, essentially what the prescale does is that it divides the clock. It makes it slower, essentially. And if it's slower, that's better. That's actually better, because we want more time. We want more time, which more times essentially means a slower time. Slower, basically. To the frequency has to be less for more time. Because of the inverse relationship. So let me just explain this again. So the count, the actual count, is multiplied. Let me just type it out underneath. Number of counts multiplied by time for one count multiplied by the prescale is equals to time required. So that's what this is. This one. That's what that is. It's nothing special or spectacular. That's all this is. Number of counts multiplied by the time for one count multiplied by this prescale. And obviously we just make this guy the subject of the formula, and that's what this is. And once we make that the subject of the formula, okay, and we come up with this particular this is what we come up with. And in this case we want 500 milliseconds, so we want 500 milliseconds delay. And the prescale I chose to be 16. You can start doing your prescale from depending on what your delay is. You can start with no prescale, and no prescale essentially means this guy is going to be 1. It's going to be, this value here is just going to be 1. And if you start with no prescale, this will be 1, and then you work your way up. Let me actually check there. So obviously these are the options you have. You have 2, 4, 8, 16, 32, 64, 128, and 256. In this case I just chose 16. I chose 16 and that was good enough. You see, as you can see too here, that's because there's an option to not choose a prescale. So once you select a prescale bit, say you want a prescale, automatically the minimum is going to be 2, the prescale. Alright, so that's that. This is the prescale, and this is the time required, which in this case is 500 milliseconds. So here we're just gonna put 0.5 there. It's gonna be the value there. It's gonna be a time in second, and FOSC will be the time in hertz. Remember, these two match up. These two, it's important that they stay the same. So if this is in megahertz, this would have to be in microseconds. Don't worry too much about that. Just leave FOSC in hertz. So if it's a 4 megahertz, you're gonna have to type 4 million hertz in your calculator. And this one, you're gonna have to keep it in seconds. So it's 0.5 seconds, just to keep everything normal. Seconds, hertz. Yeah, that's that. And once you do all that calculation, what we get is 85 ED. Let me actually quickly check what that is in the calculator. So 85 ED. So in decimal, that's 34. Just 34,285. 34,285. So that's what that is. And yeah, so this is the, so obviously for the YY, so once you convert this guy to hex, you get 85 ED. So 85 is the YY, which you write into timer 0H, and the ED, I put that there, ED is TMR 0L. I'll put that in TMR 0L, and that's how you initialize the timer. And let me not forget, for the actual T0 con, so what we do is, let me just go back to the code, data sheet. So first off, you want to enable timer 0, and next you want to say next bit number 6 is it's configured in 16-bit timer mode, and that's bit number 6, so we'll make that 0. And then the next one, timer 0 clock source select bit. So in this case we're using the internal clock. So what this one says is transition and T0 CKI pin. Well, we're not using an external clock, so we're not connecting anything to that T06 CKI pin, so we're actually using this one here, internal instruction cycle clock. So this bit is going to be 0 as well. And this particular one is not so important in this particular application anyway. So you could make this 0 or 1. I chose 0, increment on low to high transition of T0CK. Oh, sorry, my bad. This is actually unimportant. It's unimportant because we didn't choose a transition in T0CKI pin. So bit 4 is irrelevant, honestly. So so bit 3, timer 0 prescaler assignment bit. For the assignment, so we're gonna, timer 0 prescale is assigned, so that's gonna be 0. And if you don't want a prescaler, you just make this, you make bit 3 or 1. We obviously want a prescaler in this application. So, and then from bit 2 to 0, if you chose a prescaler in for bit 3, which you made that 0, then you would use the, in this case we wanted 16 prescale of 16, so we went for 0 1 1 in this case. And if you look at the code, that's what it is. The last 3 bits is 0 1 1. The one right before that is 0. So I think this is a faster way to do it, and not just state everything. Actually, on MPLAB code configurator, that's for the C version. If you're coding this in C, it does this for you automatically. It does this assignment. So I just copy and paste it from that, because it's uses, there's less instructions, to be honest. Is there less instructions? Or? Yeah, it's much faster, easier to understand. Yeah. So that's a timer 0 init, and then the UART init. To be honest with this, I don't want to go too deep into it because there's another video that actually does that. So just go check that out. Let me just give a brief overview. So here I'm just using this is a baud rate of 19,200, so that's what determines this. And yeah, and I'm just setting up the pins according to what it says in the data sheets, and according to how it describes it in the data sheet, and that's what this is. To be honest, there's a much better explanation already for this. Just check that out. For UART, initializations in general, because it's a video in itself. And for the ports, also the same thing. The port is also tied to AN2. You can check that out from table 3. Here we go up there. It's at table 3. Trying to okay. There you go on table 3. I'll just go zoom in. So you look at RA2, it's tied to AN2. So and that's until A because it's port A. And then afterwards we want digital output. So tris A2. So we're worried about tris A2, so we're gonna clear the tris A2 bit of the tris A register and clear the port. Initially we're just gonna clear it. And now let me check if I've done all the initializations. So UART init done. Oh, UART init, you're gonna have to check another video. It's, oh gosh, it's a long one, but it's worth it. Depending on how much time you have. The thing is about explaining in this video, this video is gonna be much longer than it has to be, so you just go check that out. And port init as well, port init, port ARA2. There you go. And let me just go back to and explain. All right, so for the UART. So this is a way we write strings to a terminal directly. We just write them directly to the terminal. So we have a table pointer, right? So let me just take out the notepad again. So there's a table pointer in there's a table pointer register. So for the program memory, there are several registers. So to get access to all of them, we have a table pointer. But the issue now is we have a certain amount of registers, right? So we have I believe there's about 3. Well, theoretically we could have 3 million of them. Anyway, let me just give an example on a small scale. So let's say we have 16 registers, right? Well, let me start with 8. Let's say we have 8 registers. If we wanted to identify each register, we'll just say 000, 001, 010, 100, 101, 110, 111. I think I'm missing one here. 0, 1, 2, 0, 1, 1. And this is all the possible combinations for 8 registers. So to address them, to address 8 registers, we need only 3 bits. We need a separate register to actually address it. So let's say we have 8 registers. So let's say we wanted to access each one of them. We'd have a separate register to actually store these values into, and that register only has to be a 3-bit register, right? Now imagine we have 16 bits. Now we don't have 8 registers to address anymore. We have 16 registers to address, right? Now the way we'll do that, we just say log 6. Alright, so the way we know the amount of registers we actually need to address 8 registers is we say log 8 divided by log 2, and that's 3. And also to that is 3. And for 16 it will be 4. And for 32, I think 32 is 4 as well, or 5. For 32 it's 5, and etc. and etc. So at some point the PIC program memory has so many registers that what's required for this is actually 24. So these 3 registers right here is 24 actually for the PIC. So there's 24 bits. I'm not gonna type that out. But the way to access this registers, it's broken up into 3. So TB, PTL, TR. Oh shucks. Let me just get it from here. Okay. TBL, PTRL. and that's for the lower one, that's for the lowest 8 bits, and then for the next 8 bits it's H, and then for the next 8 bits is U. Actually, for the U, I believe only 2 bits are used out of the U register, not all 8. I'm not so sure about that, but we use all 3 anyway whilst coding. So that's just a brief background understanding why these 3 registers exist. So first off, when we go back to the code, so what this does is we essentially saying right here, what we're saying here is we want to access the information that's in register number. Let me go back here. So we're concerned with register number. We're concerned with register number 0x4000. Right. So as you can see here, this is 8 bits. Let me just confirm this quickly. X4123. Yes. So this is 4 bits, 4 bits, 4 bits, 4 bits, 4 bits. And essentially in this case we're gonna store, so TBLPTRL is gonna take this, and TBLPTRH is gonna take this. Right, it's gonna take these 2, and this is the other one to take these 2. And then let's do that. So TBLPTRU will take 0, 0. So essentially we want to access one access to this particular register. So the moment we do this, right, the moment we point to this particular register, the information in that register goes to TABLAT. So the information in this particular register, let's say the information in there is like I don't know, 12. So right after we point into this, by writing this particular address to there, whatever's in that address, let's say it's 12, it's going to be automatically in TABLAT, which is table latch register. And then sorry, I skipped a step. Let me just go to string right quickly. Yes, I skipped a step. So let me just go back to explain. Okay, so there's another command. There's a command that says table read. This command right here. This command says table read star plus. So what this does is it reads whatever's been pointed to, right? So we've written this value into the table pointer register, right? So right after we've done that, then we execute this command, which is table read, and what that does is it sends 12, which is in this memory location, in the program memory. It sends that to the table TABLAT register, the table latch register, and the TBLRD, it increments this value. It increments that particular this value, so that we can read from the next register, basically. So it's going to be 0x004001, and then we're going to execute this command again. To read out of that register. Alright, so yeah, so that's that. And then so that's for So that's how we write a string basically. So in essence, all we have to do is just loop that until we read a 0. Until we read a 0 in the working register, and then once we read a 0, we can get out of the string write loop. And the main function to actually write a character to the terminal is this: call UARTWrite. Let's write here. This right here, also explained in the UART video. So this is the function to actually write a character to the terminal after initializing everything correctly, obviously. Okay, now I see you don't have to use this. Okay, you don't have to use this particular function if you're feeling up to it. If you wanna, write strings very quickly to the terminal, then go ahead and do it. Seemed like a good idea to include it, but now I see it might be a little bit, out there. But you could just go through it and see whether it's it's something you're gonna feel comfortable using in your code. It essentially just saves a lot of space. That's what it does. It saves a lot of space instead of doing it one by one and writing each character to the terminal each at a time. It saves a lot of time. So yeah, but you could do it the old method, whichever method that makes the most sense to you at this point in time, then use that one. Yeah, so that's essentially it. That's essentially the entire code. And now I'm just gonna run it and show the functionality in Proteus. Alright, go to Proteus. So we have the LED, push button, and terminal. So let me just press play. As you can see, the timer interrupt is being triggered, and that's the UART interrupt right there. As you can see, there's an echo. I'm typing on the keyboard. Key, yeah, but it does show up. That's the timer interrupt being triggered. And now if I press the push button, that's the external interrupt. As you can see there on the terminal, it says external interrupt triggered, external interrupt triggered. Obviously the timer interrupt is every 500 milliseconds. It's very eager. So yeah, let me just go external. There we go. That's it. Just go back to the code. Let me just do a brief overview of the code again. Essentially oh yeah, I forgot to go through the ISR, which is the most important of the code actually. So in the ISR code, so this is the beginning of the ISR. So first off, it checks the PIR1, the RC1IF bit of the PIR1 register, which is for the receive interrupt. So it checks that, and if this bit is set, it means you typed, you press the character on the keyboard, and what it's going to do is it's going to move that character, RCH1 is going to move that to the working register, and then it's going to call UARTWrite, and UARTWrite essentially writes it out to the terminal. There's the function that you saw down there. It writes that to the terminal, and then afterwards we clear the RC1IF flag, because yeah, we've executed what we needed to execute. We clear the RC1IF flag, and then we exit the ISR. When you exit ISR, this is it, red field. And then but if let's say when the ISR got triggered, it was not the receive interrupt, then we branch to ISR L1 instead, and then ISR L1 intcon TMR0IF, So we check this particular bit, TMR0IF. But that's for the timer, obviously. And we'll check the timer. And then if it is the timer, we're gonna skip the next line. So this is bit test function skip if set. We're gonna skip this line and jump over here. Print TMR int. And print TMR int, we point to the on the TMR int. There's a particular, this command basically makes the table pointer point to the memory location where the first character of the string, of this particular string, is located, TMR int, where it's located. And then it jumps there, and right afterwards we go to string write, which reads that memory location with this and increments the counter, the pointer, which is tblptr, table pointer. It reads it, and once it reads it, it's in tablat, and then it moves that to the working register. And after it moves that to the working register, we'll basically check if it's 0, because at the end of each string we find a 0. So what this does is it says branches 0, BZ. So it's going to branch to this point here if the working register, if the content of the working register is 0. So but it's not 0, so it's not gonna be BZ there. It's not gonna branch, it's not gonna return. So what it's gonna do is it's gonna call UART, it's gonna write out what's in the working register to the terminal, and then it's gonna loop, it's gonna stay in this loop right here where I'm highlighting. It's gonna stay in that loop until there's a 0 in tablet and the working register, specifically the working register, because that's all this line requires. So once it finds a 0 in the working register, it's going to branch to this line, and that's the end of the string write. So let me just explain that again quickly. So first off, you want to point to alright, so let me just explain this again. So first off, what you want to do is we're gonna point to the particular the location of the first character of the string. We're gonna point to it with this. So this command basically points to the first character of the TMR int string, and then after it does that, after we point to that TMR int character, the first character of the TMR int string, we'll call the string write function. And what the string write function does is it reads that particular memory location. It reads it, and then once it reads it, it's in the tablat register, and then we'll move that to the working register, and we check if it's 0. If it's not 0, we'll write that to the UART, and then we branch to the string write, and this loop continues until the value is 0, and then we'll return, and that's it. That is it. Okay. And yeah. So alright, so anyway, that's just for the TMR int part, and then it's gonna write that out to the terminal, and then afterwards what we do is we clear the intcon, the timer 0 flag of the intcon register, and then we stop the timer because it's been counting. We stop it, and then we reload it because we want it to start from here again. We don't want it starting from 0. We want it to start from this point right here, and then we start the timer again, and we exit ISR so that it does it again. And then afterwards, so let's say, now let's look at the other scenario where it wasn't the interrupt is triggered, but it wasn't the receive interrupt. It was not the timer interrupt. So what do? We branch to this location, and then we do that. Int 0IF. Int 0IF. And then what do we do there? If we skip if set, if this particular bit was set, we skip this line, and then we print the external interrupt message. Print that message, and then we exit. And then we clear the interrupt, and then we exit the ISR. We clear the interrupt flag, and then we exit the ISR. So first off, we check the receive. If it's not the receive, we check the timer. If it's not the timer, we check the external interrupt. And that's it. That is it. That's all. Yeah. So that's the entire code, and alright. Let me just make sure I got everything. And obviously check out the interrupt code. Let me just put a comment here. Load the pointer location. And then write string to terminal. Let me just go here. Read pointer location and increment pointer. To working range. If brown redo the loop if JBLT is not 0. Yeah, that's it. Hope that makes sense. That's the entire code. Right. Thanks for watching.